Welcome back, Calculus BC. I hope everybody's doing well. This is the beginning of a new unit. It's really a continuation of the stuff that we did. I've got my calculator here ready to go, so brace yourself. We're going to do a little bit of technology here before we get started. I want to congratulate everybody for having done the test. One new thing, update on grades. Just this morning we were told that all the grades are going to be the same. So it's all going to be daily grades from here on out. So I'll change your test grade back to a daily grade. In a way that's good, but in a way it kind of makes all the grades important. Because before, some of you would use the discovery method on quizzes to discover what was going to be on tests, and then apply yourselves to just learn that bit that, especially now with limited quizzing and testing capability, there's that. So we'll shoot for one grade a week. It will probably be in a quiz form, but I'm also contemplating how to do a review, so stay tuned on that. I'm leaning towards using the AP Classroom. So if you want, I've already opened up some of the units, I think 1, 2, and 3, all the free response questions in those self-progress check. So it's really going to be at your own pace. We've got really one more topic that we have to cover on this year's reduced set of questions for the AP test, and that is the beginning of Taylor polynomials. In fact, I printed out their blurb on this. This is the last topic specifically, and it doesn't make a lot of sense now, but it's pretty defined in the scope. So even though I probably will go on and teach you more because I want you ready for college, this is probably where we're going to end the required material, and then I'll figure out a time to cover that. So there it is. Doesn't mean anything to us, I understand that, but this is the last topic that will be on this year's AP test. And I'm going to stretch it out for a couple days. Today's I'm kind of calling Taylor Polynomials Intro or Taylor Polynomials 1. Tomorrow we'll have another lesson. The next day we'll have a worksheet practice, and I've got those coming to Canvas too. So we're up to day 11, I believe, in our online adventure. This first thing I want to start with, and this lesson it might go a little bit longer because I really want to make sure that we're understanding what it all is getting to. Taylor functions can be used to approximate other elementary functions such as sine of x, e to the x, log of x on your calculator, and this is what I'm going to do. First I'm going to check, and yep, good, you can see it, and I'm going to try to make sure that you can see this but also see what we're typing in here, and the glare isn't too bad. So first thing, please make sure that your calculator is in radians mode. So we've got that. Y equals sine of x. I've got that one already typed in. You can see I was practicing a little bit. I'm going to clear this out and just going to compare with x. Sine of x and x. I know here it says x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. It's like, how did they come up with that? Well, we'll talk about that in just a second. For now, just kind of, this is motivating our lesson. But I think if you understand and see these pictures right now, you'll get what we're talking about. First thing I'm going to go to do is graph, but before I'm going to pick zoom decimal, because that's usually what I want us to start with. Zoom decimal, and I've got the graph. There's sine, there's sine, there's sine, up and down, up and down, up and down, and good old y equals x. So what we're saying is that is good enough, really, to estimate. Isn't that pretty crazy? From here to here. So it looks like about from negative pi over 2 to pi over 2, sine goes up to 1. Let's change our window now to be negative pi over 2 to positive pi over 2. And, whoops, go to, whoops, yeah, I got to fix that, don't I? There it is, to positive pi over 2. And I'm going to change my y min and y max because sine and cosine are going to stop at negative 1 to 1. So let's make it from negative 1 to 1. Oops, to 1. There it is. And graph that. And if you look at those two, remember I've got these two graphing simultaneously. You can see the line and you can see the graph. It really is pretty close. I mean, dang, right there it's pretty close. But as we add more terms, let's see what happens. So now I'm going to go back to y equals, and I'm going to increase a term here and say minus green y equals, oops, to get our fancy fractions here, x to the third is what that says, over 3 factorial. And remember, 3 factorial means 3 times 2 times 1, right? We need to understand and be good with factorial. It is in your calculator, so that's a probability problem. So math, probability, factorial. Okay, I'm just going to graph that. And you can see, I don't remember if you remembered before, it went straight on. Well, now it's syncing up a little better, but then it diverges off a little bit. Or if I change my window out to even, I don't know, we could change it pi to negative pi to pi this time. Let's see how close. Whoops, did that again, didn't I? Negative pi to pi. Let's graph that. So you can see that the sine wave is this one here. It's going to come back down and hit it pi there. But the third power one is pretty close from here to here. Wow, that's pretty close. I'm going to add another term here, and let's compare that. So plus green y equals x to the fifth. And again, we'll see how these are derived, so don't worry about how am I getting these terms. These are the last thing if you're thinking, oh, he's just typing in random stuff. Clearly, this has been well thought out by geniuses more genius than all of us combined. So hats off to Mr. Taylor and Mr. McLaren. We're going to see both those names here in just a second. Math, probability, factorial, and graph those two. And you can see that it's like, oh, as the kids might say, that's pretty tight there, comparing those two in a certain window. Okay? So, in fact, spoiler alert, this is actually how your calculator calculates these. As ashamed as I am to say it, your calculator does not know the unit circle. I know that's appalling. Your calculator, clearly with a lot more terms than just these 3, is using a Taylor polynomial to not only approximate, but with pretty good accuracy, as you can see. These clearly with more than just the 3 terms, it's able to calculate those and use those to calculate those sine graphs, e to the x graphs, log of x graphs, lots of different graphs. Okay, so that's our motivation. That's why we're doing it. And there's lots of cool things that you can do. What you can see and where we need to get to eventually this. Was it a pain to maybe take the derivative of sine? Sure. I mean, we could do it, but it was fine. But can we all take derivatives of these kinds of terms? Yeah, bring the power down, bring the power down. Could you all take the integral of this? Increase the power, divide by the power. There's all kinds of reasons why these Taylor polynomials are good to go. It's a bit of a shame that we won't be tested on that, because that would be the next step. Why do we need all these? Well, we can take derivatives. We can find all kinds of cool functions there. But I'll continue on with that, so not to worry. Okay? So that's our motivation. Now, Taylor polynomial definition. If f has n derivatives, so clearly we're taking a bunch of derivatives here, because you can see how these are generated here in just a second. At x equals c, we're going to say where that is centered, okay, and you'll see that where we come up with 2. Then the polynomial, a polynomial of n equals the function value of our original function plus the first derivative at that value times x minus c plus the second derivative, so that's f dash dash there, at c divided by 2 factorial times x minus c squared plus dot dot dot. So the third derivative over 3 factorial times x minus c to the third, dot, 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 etc., etc. The nth derivative at x equals c divided by n factorial times x minus c to the nth power. This is called an nth degree Taylor polynomial for f at c, and it's named after Brooke Taylor, an English mathematician. Okay, so Brooke Taylor, mate. I know that sounded a little more Australian, but pretend. If c equals 0, this is a special one. Again, so it's all the same thing, but now we've got at x equals c, it's now at x equals 0, f prime at x equals 0 times x to the 0 power, which is 1, x squared over 2 factorial, there it is, x to the nth derivative divided by n factorial. That's called an nth degree Maclaurin polynomial, named after another English mathematician, Colin Maclaurin. Okay, so two substantial folks in the math world. This is the first one. Let's do this first one. Find the Maclaurin polynomial for n equals 6 for the cosine function. We just did a visual of the sine function. Let's see if we can find the cosine function. Then use the 6th degree polynomial to approximate the value of cosine of 0.1. Well, we know what the cosine of 0 is. It's 1. We all know that from the unit circle. But can you imagine that there would be other values of cosine that you could find and calculate, and away you go? So let's do this. First thing, I'm going to set Maclaurin. That's my trigger to remember that that means c equals 0. So I'm going to write that down. Maclaurin, c equals 0, bam. Then I'm going to make a list of derivatives. Well, I'm starting out with cosine of x, because that's what I'm trying to find. So I need to find f of 0, and we'll make a table here. Okay? Then f prime of x, because I need the 6th degree, the 6th term there. So I need to make a big long list here. So use your college-bound handwriting. You should be able to do this. What's the derivative of cosine? Well, that's negative sine of x. Cool. F double prime of x equals the derivative of negative sine. Well, that's negative cosine. That's cool too. The 3rd degree, or 3rd derivative there, is going to be the derivative of negative cosine, so that goes back to sine of x there. And after the 3rd degree, we're just going to put little parentheses there, because not f dash 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 and f dash or 5 or whatever. V, yeah, just the number there is fine. Equals of x, sorry. Equals what? What's the 4th derivative? So we're back to cosine. And can you see that this is just going to repeat the same pattern? So after a while, you shouldn't need to generate an exhaustive list if we want the 6, but we'll keep that in mind that we're going up to the 6th power. Since c equals 0, I'm also going to calculate f of 0, which is the cosine of 0, which is 1. F prime of 0, which is the negative sine of 0, well, sine of 0 is 0, so negative 0, 0, 0. F double prime at 0, that's negative cosine of 0, which is negative 1. F third at 0. Okay, so that's the sine of 0, back to 0. And then F4, the 4th derivative at 0, is equal to, well, that's just cosine of 0 again, is 1. So can you see these patterns repeating? 1, 0, negative 1, 0, 1, 0, negative 1, 0. I'm going to repeat the repeat. Okay? So what I'm doing is building up the terms that I need. I could look at this one, but since I'm building a Taylor, or not a Taylor, but a Maclaurin at f equals 0. And really, at c equals 0 is just a special case of this. So if you look at that, it's just working that way. Okay? Special case. So I want to make my 6th degree polynomial. So now it's time to start building my 6th degree polynomial. Well, that's f of 0. If anything, sometimes in years past, people forget that first one. So you got to remember, it's f of 0 plus, if you want to say x to the 0 power, which is 1, that's fine. This is x to the 1st power over 1 factorial. That's fine. F to the 2nd power, or the 2nd derivative, sorry, times x to the 2nd power over 2 factorial. So all those coefficients and powers and derivatives and factorials all match up. Okay? So there it is. There's the general term. The nth derivative at that value, in this case 0, times x to the nth power divided by n factorial. They all should match. We're just using this to build our table here. Well, f prime at 0, right? That's what it is, times x. Since it's a Maclaurin, we can just say times x, plus what? Well, let's see. F double prime at 0, x squared over 2 factorial, plus, let's do another one, f to the 3rd, 0, x to the 3rd over 3 factorial. Okay, dot, dot, dot. After a while, you should be seeing the pattern here. So let's plug in some information. Cosine of 0 is 1. plus my next derivative is 0. So do I even need that? Well, this first time we'll write it. This next time we won't need it. The second derivative is -1 x squared over 2 factorial. Plus my third derivative, since I made my table here, third derivative is 0, so 0 times who cares, plus the fourth derivative is 1, x to the fourth over 4 factorial. Are you starting to see a pattern? The next derivative is going to be 0, right? Because we're repeating this pattern. 1, 0, -1 would be our next one. -1, x to the 6th over 6 factorial. Do we know when to stop? Well, sure we do, because we wanted a 6th degree polynomial. There's our 6th degree polynomial there. Okay, so clean things up, and we'd get p to the 6 as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And yes, there will be patterns, yes. In a normal year, you would be expected to memorize these. I bet they'll find clever ways to have you use these, but you could still have your notes and access to the polynomials in your book. So I'm not sure. That's one of the things that I've got on my list of things is think clever ways to pull as many questions that they're going to be asking you. So I'll work on that after we finish the new material. So do I have a 6th degree polynomial? I sure do, because it's 6 degrees. It's got 4 terms, but it's got x to the 6th. Okay, I want to use the 6th degree polynomial to estimate the cosine of 0.1. Well, that's 1 minus 0.1 squared over 2 factorial plus 0.1 to the 4th over 4 factorial minus 0.1 to the 6th over 6 factorial. And plugging in your calculator, that would be a time for calculator time, of course, 0.99504. Okay, and yeah, for these you probably will need more than 1 decimal place, or more than 3 decimal places, because that's the whole point. We're going to be seeing how closely they're going to estimate that. Okay, so what we're saying is that the cosine of 0.1 equals that. Well, you know what? I'm just curious. Can't help it. Cosine of 0.1. If you assume that I typed in this correctly, and I'm not going to take the time, if you want to, I'm pretty comfortable that that was the right answer that I got. 0.99504. Oops, I missed an extra 0. And that is in my notes, so not to worry. There was an extra 0 there. My bad. 0.99504. I said it. 0.995004. But then it went on and on and on if you needed more decimal places. So you've got that. Okay? So there's that one. Cosine. So not only did we figure out how to build it, moving forward, you would be expected to have that one, and I'll show you patterns on how you'll learn those tomorrow. This next one, find the Taylor polynomial of n equals 6 at log of x at c equals 1, then use the 6th degree polynomial to approximate the log of 1.1. So a lot like this one, but now we're using log. So here, c equals 1. F of x equals log of x. F prime of x equals 1 over x. Right? Right, the derivative of log is 1 over x, we know this. The second derivative of x equals, well, x to the -1, bring the power down, bring the power down. I bet we've done this so many times it'd be -1 over x squared, sorry. -1 over x squared. This next one would be, remember, you could make that -1 x to the 2, so you can bring the power down. Third derivative is going to be negative, becomes a positive 2 now, x to the -3. F4, so not seeing the same pattern yet, but we'll see some patterns, so not to worry. That's going to be -6, x to the -4th. So if you're not sure where I got that, x to the -2. Oops. So Yeah, you can see that makes that positive. This is equal to x to the negative 1. Yeah, you got it now. And the fifth degree derivative, or the fifth derivative of this, so we can take this derivative again and again and again. That's going to be 24 x to the negative 5. And the last one, the sixth derivative here of our log function, is that negative 5 times 24, negative 120, x to the negative 6th. Now, so let's make a table here. F of 1, because that's where c is equal to 1, so f of 1. Well, what's the log of 1? 0. F prime of 1. What's 1 over 1? 1. F double prime of 1. So clearly the numbers there are going to be, 1 is going to be easy to see. That's negative 1, isn't it? Okay. What about F double triple prime? That's going to be positive 2. F, fourth derivative here. Negative 6. And the fifth derivative, positive 24. The sixth derivative, negative 120. Now for those folks that see patterns, I really like this idea. This is f of 1, so that's okay. Remember, up here, we need the derivative, and we're also cooking in with factorials. So I'm going to rewrite this as a factorial. Believe it or not, this is 0 factorial. Believe it or not, this is negative 1 factorial. This is 2 factorial. This is negative 3 factorial. This is 4 factorial. And this is negative 5 factorial. That's going to be handy to see those patterns in just a second. Okay. Questions there? Well, this is where we'd see some questions. But there's our setup. Let's do our 6th degree polynomial for the log function. Remember, we need f of 0, or in the case this is f of 1, so our starting point f of 1 is 0, plus the first derivative, which is 1, times x minus 1, plus the second derivative, which is negative 1, over 2 factorial, times x minus 1 squared, plus 2 factorial, which is 2, over 3 factorial, times x minus 1 to the third. And then we got a minus sign, so that's minus 3 factorial over 4 factorial, x minus 1, sorry, to the fourth, plus 4 factorial over 5 factorial, x minus 1 to the fifth, plus one more term, minus 5 factorial, that's the 6th degree, or 6th derivative there, minus 5 factorial, over 6 factorial, x minus 1 to the 6th. Clean all that up. Well, 0 is not hard. 1 times x minus 1, cool. What do you get here? Well, 1 over 2, isn't that just going to be x minus 1 over 2? 2 factorial over 3 factorial, isn't that just going to be over 3? But this one's positive. 1/3 x minus 1. This was a score. No? This is a 2. This is 3. Minus 1/4 x minus 1 to the fourth, plus 1/5 x minus 1 to the fifth, minus 1/6 x minus 1 to the sixth. I see a pattern here. Okay, I see a pattern. We've got all the terms, they alternate in signs, but I've got all the powers. Before with cosine, we derived it, we saw we only had even powers. With the sign that we just tried with our calculator, we saw all the odd powers. Here we're seeing all the even powers. For cosine, we're seeing every power, but they're alternating signs in all three of those examples here. And all the factorial business seems to divide out except for the last term. So you've got the degree here divided by 6. Well, using that, you'd get 1.1 would be 0.09531, and using my calculator of 1.1 with the same number of decimal places, we'd get 0.09531. So a 6-degree polynomial for this function centered at 1 would be a good estimate to help us calculate the approximation at 1.1. Clearly, you're not going to calculate the log of 18 if you've got it centered at c equals 1. You might want to get it closer to log of 18, but that's the whole point. We're going to be finding those values, and that's why I used the calculator to kind of show you, well, right within that window there, it's really close. We'll talk about where those would converge and diverge. Okay? This next one, and this typically is a question that shows up on the AP test every year, so I would put a star by this. They might find a clever way to do this. Suppose that g is some function we don't know about, and it has continuous derivatives. In other words, we can take the derivatives of that forever and ever and ever. There's no sharp turn where there wouldn't be a derivative there. The first derivative, second derivative, third derivative, fourth derivative are all given to us, okay? And that g of 2 equals 3, g prime of 2 equals this, that, and the other. We've got g double prime and g triple prime. Write the Taylor polynomial of degree 3 for g centered at 2. That means c equals 2. So the third degree polynomial is my first value, g of 2, right, which is 3. Right there it is. Plus my second term comes from the first derivative, negative 4, times x minus 2, because it's centered at c equals 2, divided by 1 factorial. Right? We've got x minus 1 to the x minus 2, sorry, to the first power. We've got 1 factorial to jive with that. Plus my second derivative, so this is going to be my x minus 2 to the second power, but my second derivative there is 7 times x minus 2 squared. But I need to remember to divide that by 2 factorial, because that's the second term, the second derivative, the second factorial, factorial 2. Plus, again, negative 5 is my third derivative. This is x minus 2 to the third power over 3 factorial. Clean this up. 3. 1 factorial is just 1, so minus 4 times x minus 2. Do not expand this out. Heavens no, because this is the whole point. We should have a bunch of x minus 2, x minus 2, x minus 2, x minus 2. This will be plus 7 over 2. X minus 2 squared. And this will be negative 5 over what, though? What's 3 factorial? Minus 5 sixths. X minus 2 to the third power. Okay? This next one is a great one, because now we're giving you e to the x equals this. And tomorrow we'll review how we know that, but e to the x is this one. E to the x is the all of the terms are positive, and there's all the terms there. Sine was all the odd terms. Cosine was all the even terms. Remember, e to the x increases, so it should make sense that we're just increasing. Okay, or, yeah, increasing like this, sorry. Exponential function there. But I want to build this up. E to the x minus 1 over 2x, and I want to take the limit of that. It's like, what? This is really cool. All we're doing is plugging these terms in for this one right here. So I'm going to write the word limit. X approaches 0 of what? E to the x. Just write it down. 1 plus x squared over 2 factorial plus x to the third over 3 factorial. That much there is this right here. Okay? I mean, I didn't mean to cross off that 3, but you get it. That e to the x is that business, right? Continue the rest of my expression. Minus 1 over 2x. Well, that 1 and that minus 1 go away, so that's easy enough. Limit as x approaches 0. X plus x squared over 2 factorial plus x to the third over 3 factorial all over 2x. Well, if I divide each of those terms by x, what do you notice? This is x over x is 1, right? This is x squared over x is x over 2, so let's simplify those. In fact, I can kind of bring that 1/2 out and just do that later. 1/2. X over x is 1. Cool. Plus x squared over x. I'm canceling out my extra x's here. Is just going to be x over 2. Plus x to the third cancels with one of those x's. That's going to give me x squared over what? Well, what's 3 factorial? Isn't that going to be 6? And one more we could say as x approaches 0. 1/2 plus x over 4 plus x squared over 12. Can you take that limit? Of course you can. That term goes to 0. That term goes to 0. All you have left is 1/2. Wow. Just looking at this, I would have no idea that this is 1/2. Well, you could use L'Hopital's rule. Yeah, but isn't this a lot faster if you know that you're given this? So a lot of times, and this works because L'Hopital's rule is still true, but they'll find clever ways where L'Hopital's rule would be such a pain to use, or you wouldn't want to use that, where you could find that limit right there. So another clever way, imagine that, using Taylor approximations to plug that in. So, and it doesn't look like any of the extra terms, if we went on to the next terms, would matter because it would still be 1/2. It's still accurate enough right there. This next one is a great question because it sees if we understand this graph. Okay, so given that P2, second degree, or the second degree polynomial, is a plus bx plus cx squared, is the second degree Taylor polynomial for f at x equals 0, or about x equals 0. What can we say about the signs of a, b, and c if the graph to the right is, if f has the graph to the right? So this is the graph of f. And I always do that just to label my graph there. And you should too. Well, what is a? Isn't a my first function there? I'm going to say that a is greater than 0. Why is that? F of 0 is positive. I'm going to put it in red pen here. Isn't this my f of 0 right there? That's a positive number. We don't know what it is. There's no scale here. But we know that it's positive. I'm going to say that b is also greater than 0. Why? Because f prime of 0 is positive. What is f prime? The slope of the tangent line is positive because at x equals 0, isn't that function increasing? That slope is positive. It's increasing. Okay? Why? Because f prime is 0, is positive. F is increasing at x equals 0. So another way of saying that. F prime is positive at x equals 0. F prime is 0 is positive. And you could even say greater than 0, but I'm using that here. So what about C? Well, remember, I started my inequality here, but I'm going to pause. C is what? Has to do with the second derivative divided by some 2 factorial times x squared. So what is the second derivative of this function? It's actually going to be less than 0, isn't it? Because f double prime at 0 is negative. How do we know that? F is concave down at x equals 0. It's increasing, but at a decreasing rate. So it's increasing, but we can see concave down. That graph is concave down. Isn't this cool? Can you see why I would think this is a really cool topic that pulls a lot of stuff together? So make sure, even if you're saying, it's not going to be on the test much, this they seem to like. So I would not blow this topic off. And as we learn more about what the format of the test is going to be, we know it's going to have 2 free response questions on it. I'm sure they're going to be multi-part. You know that. But I will try to predict and use as much witchcraft as I can to discern out what I think the questions are going to be like. I think there's going to be posting examples, and they're also going to be posting a chance for you to practice the whole submission thing. So as we get closer to the end of the month here, I want everybody that's still taking the test to practice how you're going to submit, because there'll be a 5-minute submission for question 1 and a 5-minute submission time for question 2. That might be uploading your work that you're taking a picture of. It might be using the submit button if you've typed in questions on your computer or answers on the computer. Who knows? Okay, so stay tuned. This was a lot, okay? And I think this is a good start. Tomorrow we'll come back for another lesson. I posted those work notes on there in a worksheet if you want to get started on these. But kind of let this digest, think about it, and get practicing. All right? As always, signing off. I hope everybody's doing well. Stay well, isolate, and but certainly keep up with your work. The more we're working on this stuff, the less time you've got to play Animal Crossing. So it's a win-win, I think, right? Alrighty, y'all take care. Love you, mean it in a school-appropriate way, and I hope everybody's doing well. Take it easy.